let's say you deposit $1,000 into a bank account, earning interest at a rate of maybe 4% per year. Okay. Now, I could talk about the full compound interest formula where maybe that 4% is compounded quarterly or monthly or something like that. But to keep it simple, I'm not going to do that. Let's just say the actual growth rate is 4% per year. And so therefore, the exponential function that represents your balance as a function of time, I'll call it B equals F of T, B for balance in your bank account. It would be 1,000 times 1.04 to the T power. This represents an actual or effective relative rate of growth. You want to get this terminology down, of 4% per year. What does that mean? That means every year your money grows by 4%. So for example, at time 0, the balance is 1,000 because 1.04 to the 0 power is 1. Let's say in dollars. Don't forget your units. This is in dollars. After 1 year, it's supposed to grow by 4%. So the amount of interest that you get should be 4% of 1,000, which is 40. So the balance should be 1,040, and it is. 1,000 times 1.04, you can double check on your calculator, is 1,040. At time 2, it should grow by another 4%. What's 4% of 1,040? Take your calculator, type 1,040 and type 0.04 times 0.04. 4% of 1,040 is $41.60. So that's how much it should grow by. So when I use this formula with t equal to 2, this formula up here with t equal to 2, I should get 41.6 more dollars. The final balance should be $1,081.60. Let's see if that happens. Use the formula with t equal to 2. I have to compute 1.04 squared and get 1.0816, yes, times 1,000. That is $1,081.60, just like I said. Your money grew a little bit more than the first year because of compounding, because your balance got higher. It's still the same percent rate of growth, but because your balance got higher, the actual amount of growth was larger. What's 4% of this? It's $43.26. After 3 years, the balance should be that, $1,124.86. Let's see if it is with the formula. F of 3 is 1,000 times 1.04 cubed. Try it, 1.04 cubed times 1,000. You can see the connection here. Same answer, $1,124.86. That's what it means to say the actual or effective relative rate of growth is 4% per year. Your money is growing by 4% every year. Actual effective, that means the percent rate of growth is what you actually observe or effectively observe. The word relative is different, is to emphasize the rate of growth is a percent rate, not an actual rate. I'll explain what that means here in a minute. Yes, how do you rewrite this function in terms of base E? Well, what's the general approach? If you've got an arbitrary function that's exponential growth, say a times b to the t, or if you want to use the book's notation, P0 times a to the t, I think they use. It doesn't matter. We'd like to find the value of k that makes these things equal. What is k? Solve for it. You can cancel the a's. You're left with b to the t equals e to the kt. That's the same as, by a property of exponents, e to the k to the t. Can the t's cancel? Well, sort of. If this is going to be equal for all values of t, the base in both cases has to be the same. So it's sort of like canceling the t's, but people don't usually call it cancellation. You can say that b has to equal e to the k, and therefore k must be the natural log of b. So for our problem, going back up here, the b was the 1.04. Again, in the book's notation, they called that a. Don't worry about the notation. It's the idea that's important. So for our problem, this is natural log of 1.04. What does k represent? K represents a continuous, a so-called continuous relative rate of growth. And it's going to be close to the actual relative rate of growth, but not exactly the same. For our problem, again, that's natural log of 1.04. I'm predicting this is going to be a little bit less than 0.04. ln of 1.04 is, yes, a little bit less than 0.04. This is approximately 0.03922. As a percent, that's 3.922%. Algebraically speaking, it's just another way of writing the function. But what does it actually mean? Why is it called a continuous relative rate of growth? Well, once again, it is a percent rate of growth, so it is still a relative rate of growth. The continuous is related to compound interest in the fact that you can get these kind of equation from essentially compounding every second of every day continuously, instead of every year or every quarter or every month or every day or every hour or every minute or every second. You are compounding interest every moment. That's where the word continuous comes from. But what does it mean? Does it have a meaning? It does. The picture I'm about to draw is exaggerated for the sake of illustration. But I'm going to pretend I'm drawing the graph of this function. B equals f of t equals 1,000 times 1.04 to the t power, which indeed is equal, at least approximately, to 1,000 e to the 0.03922 times t power. We've just confirmed, because k is natural log of 1.04, is this, that these two things are approximately equal. On this graph, which again, I'm going to exaggerate the scales here. I'm going to exaggerate the concavity. If you drew this on your calculator, the graph would look pretty straight. It is technically an exponential function, so it's concave up. It would look pretty straight on this kind of scale, though. I'm going to make it look like it's pretty clearly concave up. That's not exactly what you would see on your calculator, though. The fact that it grew by 4% during that 1 year means that your interest is 4% of 1,000, $40. So the final balance after 1 year is 1,040, like we saw before. That's 4% growth. 4% growth. How do you interpret this 0.03922? Here's a way to do it. I'm not going to fully explain why right now. I'm going to save that for when we know about derivatives. If you drew the so-called tangent line to this curve at that point, what is the tangent line? Sometimes people think a tangent line just touches the curve at one point, but that's not quite right. That's true for circles, not necessarily true for curves. What is it? What it is more technically speaking, is it's the line that best approximates the curve near the point. If you zoomed in on this green curve near this point, it would look more and more like this red line. And this scale is now way off because this 0.03922 is essentially supposed to represent the fact that this red line grows by 3.922%. Now, if that really were the case, the red line and the green curve would be much closer together on this scale. So it's a bad drawing. The green curve would barely look curved and the red line would barely look like it's below it. I can show you it on the calculator here. Let's see, is that worth doing here? I think it's worth doing. We might not even see a difference between them. So if I did 1000 times 1.04 to the x power and compared it with a graph of a line with the appropriate slope, and it turns out the slope would end up being 1000 times this. I'm not going to explain why. So, and that's 1000 times that is going to be, trying to do that in my head here, 39.22 times x plus 1000, I believe, should be a good approximation to the equation of this red line. Not explaining why. If I go in the window 0 to 1 here in the x direction, I got to make my y scale large, say 0 to 2000, 0 to, let's go closer. Let's go 1000. Give ourselves the best chance of detecting the difference between these, to 1050. So the first graph is going to be the green curve. It's going to look pretty straight. See a slight bit of curvature to that, I think. Second graph is supposed to be the line. There, you saw it already, right? See it? Now you see it looks thicker over here. That's because it's two graphs you're seeing there, but they're very close together. So they just sort of looks like one thicker graph over here. That's what it really looks like on the scale. If you make your scale bigger, you can definitely see the difference between them. If I go out to like x equals 5 and make this go up to 1500 or something, I'm sure we'll see a difference between them on this scale. And you can definitely see more curvature in the first graph. That's the exponential growth curve. There's the line. They are two different things. Okay. This 4% actual growth and 3.922% continuous growth occurs over more than just the interval from 0 to 1. It occurs over any interval of length 1. If you start at any point in time and figure out the actual growth and also the continuous growth of the tangent line, you'll get the exact same percentages. I'm not going to take the time to verify that, but that is true. It's a fundamental fact about exponential growth. Maybe before we review for the first exam, I'll remind you of that. Okay? On exams, I often share old exam problems, and I have asked questions related to this concept, and you'll see on my sample exams that how that concept comes up in an exam problem sometimes. But yeah, here's how you convert between K and B. If you know B, you can figure out K, and equivalently, if you know K, you can figure out B. Use logarithms.